All right. Good afternoon, everyone. It is my pleasure to welcome all of you to the 2025 Hoyt C. Hottel Lectureship. And before I formally introduce our distinguished speaker for the afternoon, I'd like to say a few words about Professor Hoyt Hottel, after whom this lectureship is named. Hottel came to MIT from Indiana in 1922 at the age of 19, having just received an AB in chemistry from Indiana University, and he never left. He received the SM in chemical engineering in 1924, studying under former ChemE department head, Professor Walt Whitman. He served as his practice school station director in Buffalo in 1924 and 25, and was then an institute fellow in fuel and gas engineering before being appointed as assistant professor of fuel and gas engineering in 1928. He was promoted to associate professor in 1931 and full professor of fuel engineering in 1941. In 1965, he became the first Carbon P. Dubs Professor of Chemical Engineering, a title he held until he transitioned to Professor Emeritus in 1968. He remained active in the department until his death in 1998. Professor Hottel was a central figure at MIT, and particularly in the Department of Chemical Engineering, for more than 75 years. Professor Hottel was remembered for his intensity, intellect, and integrity. His lectures aimed to make students think. He made seminal contributions to the measurement of gas emissivity. He established the mathematical framework for the quantitative treatment of furnaces, conducted the first systematic investigation of the laminar to turbulent transition in diffusion flames, and explored heterogeneous combustion. Hottel was co-founder with Bernard Lewis and A.J. Narad of the Combustion Institute. He was elected a member of the National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences. Additional awards include the U.S. Medal of Merit, the Founders Award from the NAE, and the Founders Award and the William H. Walker Award, both from AICE. Hottel's broad interest in energy is very relevant to today's energy sustainability and climate discussions. With funding from Godfrey L. Cabot in 1938, he organized the world's first solar energy utilization research center. The studies there led to the choice of the flat plate collector as the most promising device for solar heating, and construction of the first solar heated house and 3 others, which provided data for economic assessment of solar space heating and hot water supply. Professor Hottel advocated for the logical assessment of the economic use of the sun as an energy source. And now, to introduce our guest for today, Professor Nitash Balsara. Nitash is the Charles W. Tobias Professor in Electrochemistry at UC Berkeley. He's a chemical engineer with a bachelor's degree from the Indian Institute of Technology in Kanpur, India, a master's degree from Clarkson University, and a PhD from Rensselaer Polytechnic Institute. This was followed by 2 postdoctoral appointments, one at the University of Minnesota and the other at Exxon Research and Engineering Company, or EMRE. In 1992, he joined the faculty of the Department of Chemical Engineering at Polytechnic University in Brooklyn, New York. In 2000, he moved to Berkeley to join the faculty, also in the Department of Chemical Engineering, and to join Lawrence Berkeley National Lab as a faculty scientist. And the next sentence is not one I wrote, it was given to me, presumably by Nitash. He has managed to hang on to both jobs. In addition, he co-founded 2 battery startups with his students and collaborators, CO and Blue Current. Please join me in welcoming today's and this year's Hottel lecturer, Nitash Balsara.
It's been it's just been a great day. Just meeting friends, meeting faculty for the first time, meeting the students was awesome. In the end, that's our power. So I thank you all for making me and my family feel so welcome. Chris, thank you very much. I'm going to tell you about the movement of neutral molecules under electric fields and how they are related to rechargeable batteries. My students are on the first line, and I'll introduce their work. We've had the good fortune of collaborating with senior scientists at Oak Ridge, Naresh and Eugene. Chris Stackis is at Stanford, and Jeff Reimer is a colleague of mine. John Newman is really my mentor. A lot of things that you will see here I learned from him. Rui Wong and Chao Fang are the theorists. Rui is an assistant professor in our department. So my talk has really 4 parts to it, beginning with an introduction to polymer electrolytes and ion transport. And the second part is more a microscopic molecular picture. The third is a continuum picture, and I'll get to batteries at the end. So energy density of batteries is something that everyone seems to be concerned with. And I'm going to try and get a pointer. And this is the plot of energy density, how much you carry in a liter, as a function of date. And when Sony first introduced lithium-ion batteries, they carried 200 watt-hours per liter. And that went up steadily, at least the top end. You see, at any given time, you make all sorts of batteries. And the top end is what everyone cares about. And in this nice paper, what it tells you is that since 2012 or so, this energy density has not gone up. So if you have sensed that your batteries haven't gotten that much better, whether you drive a car or carry a phone, it's true. The top end energy density has stopped increasing at any appreciable rate. Okay? The energy density is really, in the end, constrained by the electrodes in the battery, which are transition metal oxides and graphite. And one way to enable other electrodes is through the use of polymer electrolytes. Okay. So that's going to be the focus of more or less everything I will talk about. There is also a recognition of why an electrolyte can serve as a bottleneck. You see, you have 2 electrodes, and the lithium shuttles between particles shown on your left and right, and lithium enters the electrolytic phase in the middle through one electrode and then goes out the other. And as a result of that, this electrolyte develops salt concentration gradients. The electrolyte you carry in your pocket is a mixture of a salt and an organic solvent. And the salt tends to accumulate on one side from where the lithium ions are getting in, and then exits the other side. Okay. Of course, if you're not using the battery, you have some ion concentration C average. And if you apply a current, I1, let's say, which is small, you'll get concentration gradients. It's a little bit like a gas flow through a membrane, and it's just a mass transport problem. But if you drive the current high enough, what you'll find is that the concentration on the other side would start approaching 0. For example, if at this point, at this current density, this third of the electrode is not being used because there are no ions. And you can easily drive your current to a point where you don't use most of your electrode. That is called the limiting current, and that dictates whether the electrolyte can be used or not, because your device that you're powering needs a certain amount of current. If your electrolyte's limiting current is below that threshold, you can't use that electrolyte. Okay? And so limiting current is really what electrolytic work is focused on. Rather than have all these particles, I'm going to talk about a simplified battery. Can't make any money from it. It's got 0 volts. It's got 2 lithium plates. And lithium comes out of the left and goes on to the right. Okay. And those polymers are the solvent that I will be using, chains. And when you start a battery, you apply a charge, positive and negative. By definition, we're going to call the negative 0. And at positive, you get lithium ions in on the positive side. In general, your ions will be attracted towards the opposite electrode. And your electrolyte has to welcome the lithium ions that come in, but they can't welcome it too much because it has to leave the other side. It's like a little bit like a guest, in the electrolyte. Okay. And I'm going to tell you about 2 polymers. Okay. One of them is polyethylene oxide. It is There's a small industry that uses polymer-based batteries, and polyethylene oxide is what's in those batteries. And then I'm going to tell you about polypentyl melanate, or PPM. This polymer is something that we had a little bit of to do with developing it, but that's the structure. And the salt is lithium TFSI, so lithium plus with that structure carrying the minus sign. And most of the time I will be using R as a measure of concentration, which is the moles of lithium per oxygen. And it's just convenient for both polymers. Both polymers have oxygens. I'm not showing the hydrogens. They'll come into play, and so on. So we're going to try and see which of these polymers can carry a higher current. Okay? So when you take this cell and you apply current across it and measure the voltage, this is what you get for ppm. Okay? In one particular experiment, you start at a low current of 0.4 milliamps per centimeter squared. By the way, all the temperatures are 90 degrees centigrade. Okay, my lab lives at 90 degrees centigrade. When you don't hear the temperature, it's always that. And that's just because at that temperature there are no interesting thermal transitions whatsoever. That it's a simple polymer, and so on and so forth. Yeah, so you're increasing the current density, and between 0.9 and 1.1 in this case, at an R of 0.04, you see a divergence in the voltage. And that divergence is easily understood. What happens is that concentration next to the negative electrode is approaching 0. And we are used to using the Nernst equation, which is some constants that give you a voltage in the front, and a concentration of positive ions. As that goes to 0, it goes to minus infinity. But if, yeah. And so that's where the voltage is diverging. Okay. We did that at different salt concentrations. We, I mean Zach and Jay Young. And here are the data as a function of concentration. The limiting current on the y-axis is a function of concentration on the x-axis. In spite of the importance of limiting current, this is the only data set I know of limiting current as a function of salt concentration from the dilute limit all the way up to the concentrated limit. I would love to know of any other system where this has been measured. And I think it is because PEO is very easy to work with, and PPM is also easy to work with. So as you increase concentration, the current you can hold is large, and it increases because you have more and more charge carriers. But at higher concentrations, friction takes over, your transport goes to pot, and your limiting current goes down. And PPM has about twice the limiting current of PEO. Okay. I would claim that PPM is the best polymer electrolyte known to man. I would also love to be shown another electrolyte that is better. Okay. It also supports that at half the salt concentration. And that's also valuable because salt turns out to be the most expensive component of the battery, actually. All right, we're ready to move on to the next topic, which is subdiffusive motion and quasi-elastic neutron scattering. You have an ion, you have a solvent, and they're all jiggling around randomly, Brownian motion. And at long time, Brownian motion, the mean square displacement goes linearly with time. So if you were to take a particle, whichever one, and you plot it, the slope of log delta r squared versus time would be 1. That's just Brownian motion. But at small times, the mean square displacement would be a little less than 1 going with time. And that's because all materials tend to be caged for a little while. Even pure water, there's a little bit of hanging around that the molecules do before they go on their trajectory. And that transition time, you can think of as a solvation time. Okay. In a paper that I think is pioneering, Graham Fleming and company measured the solvation of ions in water. And in this beautiful paper, they showed that it is about 1 picosecond. Okay. They also have molecular dynamics simulations showing that this is true. And it doesn't matter what the details are. This is a structure factor or in some complicated sort of thing that enabled 2D IR. But you can see that the time is picoseconds, and you can see the experiment and theory agreeing. Then in 2017, one of his students, Minheo Cho, not surprisingly, showed that, in fact, lithium iron and carbonates, this is the solvent you carry in your pockets, also has a solvation time of 1 second, 1 picosecond, based on 2D NMR data that look like this. If you understand this data, you understand more about 2D NMR than me. Okay? But that's the answer. And then there came this very interesting paper from Tokmakov, who's also a Graham-Fleming student, who claimed that that paper was wrong. Okay? However, vibrational energy transfer in the absence of something hides the desired processes. They tried to measure, by the way, there were computer simulations that also gave them 1 picosecond in the previous electrolyte. Okay? So it's very common nowadays. You can't do theory without experiment, and it's vice versa. But these guys' simulation for the same system gave 100 picoseconds, both in theory and experiment. Actually, only in theory. They couldn't do the experiment because they said 2D IR fails at that 100 picosecond time scale. I'm very jealous of someone who can write a JAX paper where they just say the previous people were wrong. Right? I try to publish correct stuff in JAX, and they won't even review it. But here is a beautiful paper saying that the solvation time of the structure all of you are carrying in your pockets, we don't know whether it's 1 or 100 picoseconds. Okay? We came at it from a different technique where you measure scattering and then infer dynamics. You put a beam of some wavelength lambda into your system. These things are jiggling around. And what happens is that the energy, which is tightly controlled in the beginning, is spread because of the motion of the stuff in the scattering volume. And the energy spreads. So by measuring the spread of the energy, you can get some indication of what the motion in your system looks like. And in the case of neutrons, you're only sensitive to the motion of hydrogen, because it turns out to have an incoherent scattering cross-section that's about 100 times everything else. And when you use quasi-elastic neutron scattering, the wavelength is 1 to 5 angstroms, and so the length scale is in that vicinity. Okay? So we are watching dynamics on the angstrom length scale, and our polymers are loaded with hydrogen. Okay? So what we are looking at is how our solvent molecules are moving due to the presence of ions that we will add to it. This machine is about half the size of this room. About 10 times the size of this room. You have a little polymer sample sitting in the middle, a big neutron producer coming and banging against your sample. It's an impressive setup, if you ask me. So in polymer dynamics, the subdiffusive motion scaling is half power. Okay? I talked about the power of 1 in diffusion. For subdiffusive, it's half, and we've known this for a long, long time. There's this beautiful theory by Rouse that all of us worship in polymer science, and out of that comes this beautiful half power. And so what I'm going to show you are what I call Rouse-inspired plots. When I measure delta R squared, I'm going to normalize by t to the half so that I get a plateau of 0, so that then I can see what else is there in the system, because that's what we expect as polymer scientists. We expect Rouse to be correct. You can take neutron scattering data and on these two systems, and then look at it as a function of this R, the salt concentration. And here's the data plotted. Mean square displacement normalized by t to the half power, 0 salt, and as salt increases, you get a plateau, and the plateau comes down. And that is because of the increase in friction as you are adding salt. Okay? This is 1.5 angstrom square per nanosecond to the half power. And this we published some time ago. When we did the same experiment on ppm, as concentration increased, we saw something weird, which is that instead of the plateau, we started getting a trough, and the plateau was pushed to higher times. So the mean square displacement actually goes as a quarter, not a half power, in that early time. Following this axiom that if you have an experimental result, you can certainly find a theorist who will explain it, we turned to simulations from Rui Wong and Xiao Fang. And they simulated, there's lots of PEO simulations, not so many PPM simulations, in fact none. So we did that simulation. And here are typical structures shown. What happens in PEO is that, you see, each ion wants to be surrounded by 6 oxygens, whether it comes from water or roughly 6, 8, 5. That's the number, not 25, for example. And in PEO, most of the configurations, this is provided by one chain. Okay, so there's this gray colored chain that is all wrapping around this central lithium ion. In PPM, we have colored 2 chains because at least 2. Okay, and some of the oxygens are even recruited from the anion, which is colored yellow. And this affects transport. So if you want to be quantitative, that's the probability of a solvation structure. And you can see the most probable solvation structure has 1 PEO chain and nothing, no anion. This is a gorgeous solvation structure if you have ever seen one. And so the picture that you would draw is something like that. Okay. When you look at the PPM solvation structure, it's really fat and ugly. I shouldn't use that term, sorry. But you can all sorts of environments, 3 chains, 2 chains, at least 1 anion, and so on and so forth. Okay? So in the very simplest of scenarios, you have this cation at least in contact with 2 chains. And that is interesting because this lithium ion is serving as a temporary crosslink, a little bit like a hydrogen bond or something. And there is a rich literature on weak bonding between or temporary crosslinks in polymers. And what we are proposing is that this well-defined signature of a temporary crosslink lifetime is identical to a solvation lifetime. And so what we have proposed to the community is that you can use QUENs to get solvation lifetime, provided it's not like PEO and everything is solvated just by 1 chain. And sure enough, when you do simulations, you get the qualitative structure that I talked about, mean square displacement normalized by t to the half that goes like I showed, and very much in the high concentration limit, there's nearly quantitative agreement, 1.2 versus 1.3, a plateau. There's a lot of things that don't agree, but by and large, I think the simulations give us great confidence in our interpretation of a solvation lifetime, and it's 500 picoseconds. Okay? By the way, that half a nanosecond. So to my knowledge, this is the only correctly measured solvation time that is not 1 picosecond up to that point at 2024. So the picture is the following. As the lithium ion is heading towards the negative electrode, it carries too much of the uncharged species, and then at some point it decides to hop. Most of the literature on polymer electrolytes has been focused on this hopping, not the dragging. But the dragging is more important than the hopping, in my view. When you have 2 chains, you don't have the same constraints, and it leaves the polymer chain behind more efficiently. That's a molecular hypothesis. I have not shown you any data on transport, which I will do next. So here's my battery again. Electrodes, now I'm showing a potential that sort of goes from some value that I measure to 0, and when you don't know how something goes, you draw a straight line. Okay? And in this straight line, the gradient of the straight line matters. That drives any ion. with a charge of Z and a mobility of U, and Faraday's constant gets you the correct units. And obviously, if your charge is 0, then you'll get 0 using this formula, which is why neglecting neutral solvents is really steeped in the literature on electrochemical systems. I'll show you some 2022 paper from Arnav Latz. I mean, I think he's one of the leading theorists in Japan, if not in Germany, if not the leading theorist. And they claim that when an ion is dragged in an electric field, let's say the negative ion, I don't know which one, but oh yeah, the positive ion goes here, 3 negative ions are recruited and brought here. They don't even bring the solvent into the picture. You can argue whether this is correct or wrong, but for the moment, I just want you to say that there's no solvent. Anyway, the solvent is just there. And in fact, they talk about all sorts of problems about compressibility and flux, and so on and so forth. But I argued that when you pass current, you must get accumulation of salt on one side, which means the polymer has had to have gone to the other side. And so this motion is just part of the battery, and we need to understand that better. The way anyone understands anything in electrolyte is you go and read John Newman's book. Okay? So this, I'm going to call it the Newman book. And in that, there's this beautiful equation for the change of concentration under an electric field. C is the concentration, this is the velocity of the solvent, which is a polymer in our case. Diffusion coefficient, there's a current hidden in there. There's no voltage, for example, and T plus 0 is a transference number, which I will talk about in detail. That will bore you by the time I'm done. But I want to tell you whether this equation for chemical engineers at least is not that scary. It really talks about a control volume and what goes in and out of your control volume. The first point is that there's an accumulation term. So if there's an imbalance, then the concentration in that control volume must go up. The second term tells you the salt that is carried by the solvent, C times V0. The third part has to do with diffusion, just ordinary diffusion. Put an ink drop in water and watch it go away. That's the law, you would say. And the final is pure Newman. It's how the current interplays with this concentration field in the form of this dot product of I times the grad of T plus 0. There were some standard approximations, I would say, that were made in this field up to about 2016 or so, which is to say the solvent is not that important, and so we'll set that term to 0. And that the transference number, which is a ratio of currents, it turns out, is also independent of concentration. It's a very hard thing to measure, big error bars. So you say if it's independent of temperature, that term drops out, and the diffusion is, it just boils down to diffusion. And this is the only theoretical paper in the Nobel report on lithium-ion batteries. And that's the assumption which is used to model all lithium batteries. Okay? So I went to John and I said, what if the solvent is not, while velocity is not negligible, what should we do? And he said, Nitash, you have 2 variables, you need another equation. So he said, where in your book is the second equation? He said, it doesn't exist in the book. You have to derive it. I said, all right. COVID came along, so I brushed up on how people get 2 equations in transport problems. And I remembered that del dot V equals 0 was something I learned as an undergraduate. Okay, I carry my undergraduate books with me, and this is like that look like this, you have that control volume, and here I'm just thinking of flow. And if there is no accumulation, the simplest version of the continuity equation is del dot V equals 0. I will argue that the day you understand that this is what goes in, comes out, you become a chemical engineer. Okay? If you're comfortable with that notion, that's what chemical engineering is, in my view. How is this modified by ionic current is the question. Okay? And so during COVID, I had nothing better to do, so I sat down and I started deriving things. I came up with the equation for what del dot V0 looks like in the presence of current. has the same terms. And in this paper that I'm very proud of, we wrote that out. It has no tables, no figures, just a derivation. Now we have these two equations with which we can start actually quantifying the transport of the neutral species, because when you just use mobilities, you would always get 0. And there were some things very simple that came out that I'm surprised that the field had lost track of. For example, initially you have a uniform concentration, and you ask, what is the velocity of the species at t equals 0? And here you write them down, okay, for the first time. The first term, for example, for the velocity of the cation, related to the transference, this has been known for a long time. But the second term is not at all negligible, and one that I derived. Similarly, the negative ion and the solvent. So the bottom line is this, okay? You have an electric field. The cation and anion are not symmetric at all in many respects. And when they start moving, whatever is left has to be taken up by the solvent. It's not negligible at all when any anion moves. And the extent to which it was negligible or not was never actually measured or actually predicted. VE, by the way, is the molar volume of the salt, never 0, a partial molar volume of the salt, which is never 0. So I want to come back and tell you about our tribulations of measuring this transference number, t plus 0. Okay? So there was a conventional way to measure it, and we took as many pains as we could, measured this quantity in the way that Newman taught us, actually, which is that you have to measure the diffusion coefficient and the thermodynamic factor and all this stuff. And at the end, you get this quantity t plus 0. And we did it for different polymers reported in this paper. And you see the data. It got lots of error bars. You will see much cleaner data in the literature, but with no error bars, because they don't tell you what the uncertainty is. Okay? And one thing that struck us was that this transference number, at near the peak of the of the conductivity, is actually negative. Okay? This caused a lot of, a little bit of a turmoil. Here's a paper where our paper is part of this, in the abstract, and essentially saying that our method is wrong and our measurements are wrong and our interpretation is wrong. Everything is wrong. For example, they say, in all cases, the drift of lithium is opposite, and it indicates mostly uncorrelated ion motion. Okay? If you have uncorrelated ion motion, t plus 0 should be positive. Okay? But I'm so happy. I have never given this talk at MIT, but I always show this paper that came out of MIT, where they developed a new technique for getting transference numbers. And they say, our newly developed approach, we're able to reproduce recent experimental results about negative cation transference numbers. Okay. So not only were we given some credit, this is our work that apparently motivated them. It was, yeah. And by the way, transport by this time in PO had been studied for 50 years. Okay? So the idea that somehow the sign of one of the parameters was not known should surprise folks at least. In that picture, what they showed, and this is a very useful plot, they showed the probability of making different kinds of clusters in this PO. You see, when you have one charge, it's Ohm's law, and you learned this in high school. If you have two charges, you have an infinitum of possibilities. And here they have enumerated some of these clusters, charged, uncharged, and so on and so forth. And what they said is that most of the clusters tend to drift towards the negative side. And these negative clusters carry the cation with it at a rate that is higher than the free cation. And that was their hypothesis for a negative transference number. In fact, if you read the previous paper, you'll see that they even argue that negative transference numbers are impossible because we don't know what we're doing. but it's not true. The two oppositely charged ion net flux can be towards the same electrode, and there is no violation of anything at t equals 0. Okay? It can't persist beyond that because charge neutrality has to come in, and we know how to do that. So we turn to electrophoretic NMR to measure these velocities. Now, the ion motion. It's just like NMR, except now you have electrodes in the tube. So we are stuck with sort of only studying what we can put into this, this sort of tube. And I told you, that this is the formal definition of cation transference. The cation transference number is the fraction of current carried by the cation. So usually current is carried by cation and anion. And so it's a fraction of carried by the cation relative to the solvent velocity in an electrolyte of uniform concentration. Every one of those words that John wrote down are precious. We all know that current is Faraday's constant times velocity times concentration. Okay. The problem is that you need a reference frame for any time you measure velocity. It's especially true if you're driving a Tesla, right? You don't want to stand on the road and measure the ion velocity. So there has to be some reference frame. And the gurus of the field chose the solvent as the reference frame. And the reason why the solvent has been ignored is because everybody has been sitting on the molecule and saying it doesn't move. Okay? It's actually almost like that, not quite that bad. But if you now take this ratio of currents, you get a transference number that is this sum, the cation velocity minus the solvent divided by the cation minus the anion. The anion moves in the opposite direction, so the denominator is positive. The solvent usually moves with the cation, and so that numerator can be negative or positive. And in fact, David Hallett measured these velocities as a function of salt concentration. There's where R is. And you can see as salt concentration increases, the velocity goes down. Solvent velocity goes up. And there comes a point at which they're actually equal and close to reversing. Okay. And here is this anion velocity. And so we can, from these measurements, get transference numbers with accuracy that we can't get from other approaches. And so here is the eNMR data, this weird sort of hump all the way to 0 and then rising up. Those are MD simulations. And this critical concentration is about 0.1. This material is a small molecular weight PEO. It's tetraglyme. It's 4 units because that's all we can easily put in the NMR cell. We can put an 8-mer too, as Julia knows. Yeah, so this is the shape we get. And so when you have when you have a lithium ion, it needs 5 oxygens around it, so it drags 2 chains with it. And when you ask the question, when is this construct pervading the entire cell, you'll get R 0.1. Okay? So using this simple idea that the solvent is being dragged by the solvation shell, you would get a transference number of 0 at 0.1, and we measure it at 0.08. Of course, that's because of complexities. And I want to tell you that this shape is not that different from the shape we drew for PEO, except that the minimum is at 0.14. And that's because we needed 2 molecules of tetraglyme. We need only 1 molecule of PEO. And if you do the math, you would get 0.17 for this minimum. And so all of this terrible performance of polymer electrolytes was coming from a limited transference. We took the Franz Leonard approach to quantifying clusters in simulations. They were all negative as seen, but we also kept track of the solvent content. And it turns out that how much solvent you're moving in the cluster is also very important. In fact, more important than the ions. The last thing I want to tell you about is this crazy experiment of Emily Abdo and Chris Takis, where what you do is take a lithium-lithium symmetric cell and take X-ray images, and you do the normalization in such a way that when you take a picture, you actually get the salt concentration. It's literally dark light, and then you quantify it. So what you're seeing here is a movie of salt concentration as a function of time. Okay, you can see initially, and it goes back and forth. It's sort of uniform at some time. It's now uniform, and now the gradients are developing from the top and the bottom, and eventually saturating. Okay? So you're seeing that as real time goes by, this is experimental data, okay, of how these gradients are developing. In the top of this electrode, the lithium ions are coming, and the concentration is going up from average. In the bottom, the concentration is going down from the average, and we have this in situ data at ridiculous sort of resolution. Okay. So I said, Emily, there must be some way to get to solvent velocities just using that data. And then she reminded me, yes, here's the equation. Accumulate what solvent that comes in from one side must either leave the other side or get accumulated. And if I know C0 as a function of x and t, we have V0 as a function of x and t. Okay. So this is concentration at the midpoint. Midpoint actually is it almost doesn't change, so it's very critical. But you can see the quality of the data and the resolution and that fit. So we get a fit from which we get the velocities. So with no adjustable parameters, we are seeing how the solvent velocity initially starts at a value dictated by the transference number and eventually goes to 0. So this is the first spatially resolved velocity profile of neutral species under electric fields as a function of space and time you've ever seen. And not rocket science. There's another thing that's interesting. I've talked about concentration as a function of space and time, but the electric potential is also varying from some value to 0 in some way. At the simplest case, you can say a potential is, again, Nernst equation, so the log of this concentration must have potential. But you want to do a little better than that. You have some wires to measure the potential. So the question was, well, can we measure potential as a function of x and time? And of course, what you would really like to do is to take a reversible reference electrode, lithium wires, for example, where you have a reversible reaction, and then you measure the potential using that reversible reaction relative to a reference, and we just take that electrode on that side as the reference. And here again, Emily, this is a little bit, you need to know Newman to actually get to these equations. But Emily derived this equation. If you have a current flowing through this electrolyte, the potential drop has two components, an ohmic component and a concentration polarization component. So if you know kappa, conductivity, transference number, and gamma plus minus is the activity coefficient, and I haven't belabored this, we know all these as a function of concentration. If you know these as a function of concentration, you can back out the potential without taking a look at your potentiostat. And you know the potential everywhere. So initially, this is at constant current. The potential on the left side is low. That's the gradient of the potential, and then it grows up as a function of time, and that's the steady state potential that Emily gets. Okay. It has two contributions. The ohmic, given by the conductivity, plotted here, and the concentration over potential plotted here. And you can see that the ohmic term is 0.04 volts. This is 0.25 volts. It's completely dominated by transference and activity coefficients. You might as well not measure the conductivity. Okay? I would say improving conductivity, at least relative to PEO, is pointless. You will not affect the voltage at high currents. You need to do something about the transference, which is what PPM allows you to do. In the few minutes that I might have, I'm going to tell you how this is all relevant to solid batteries. This is the state of affairs of liquid batteries, and we argued that perhaps solids can affect that. This is a paper that launched 1,000 ships. Okay, it came out in 2012. Beautiful paper out of Kano's group in Japan, and they produced this amazing plot of conductivity. The parameters I just said are not that important as a function of temperature. And they presented this new lithium germanium solid electrolyte. And of course, they also showed in that same plot the polymer electrolyte that I've been talking about. And if you ask someone, which electrolyte would you like to work on or commercialize, this lousy one at the bottom that I've been telling you all about, or this amazing one at the top, you can imagine that most companies in 2012 jumped on the one at the top and made all sorts of announcements that you can't even find anymore. So this is an announcement from Toyota saying that their first solid vehicles would go on sale by 2025. I don't know anyone who has a Toyota with a solid battery. I don't think I'll find one by December 31st. In fact, there was an announcement identical to this in 2017. I couldn't find it in the, I remember reading it. You can buy stock. There are publicly traded startups in the solid state arena that you can buy. And really, this is an amazing thing, and I have to thank Yet for showing us that we can do this. He was the first of us that started a company and took it so far that even, I read in the New York Times sometimes about what you did, and it's just amazing. And many of us have benefited from that directly. The trouble with the Kano kind of electrolyte, the Kano electrolyte is like it's an inorganic solid. It looks beautiful when you start the battery. Right? This is my battery. You have two solids that I'm showing in a simple way. And let's say the anode is lithiated and the cathode is not. And now the ions go from the top to the bottom. You have to leave behind a gap. These particles are often 1 micron big, maybe sometimes 50 microns big, maybe 20 nanometers big. A gap of 1 nanometer is a complete insulator. There is no way a battery with particles can ever work with a classical solid by itself, right? Polymers, on the other hand, can adhere to surfaces as they as they move apart. You step on chewing gum, and you have to remove it from your shoe, even though it wasn't there on your shoe to begin with. I don't believe that all solid batteries will ever be built without a polymeric solid in it. So you're going to have to use the best polymeric solid the polymer electrolyte community gives you. Otherwise, you're never going to make one. So the last thing I want to say is, of course, why we are making batteries is because of the relevance to energy and how to do it without CO2. And I wanted to, when I got the notification that I was going to be the Hottel lecturer, I was first of all, I said, you know what? I think I've seen that name before. And in my undergraduate notebook, I realized, and this is the book actually, if you want to come and look at it, and I was learning about radiative heat transfer. I'm amazed at everything that I've forgotten. I mean, I can't, but there it is, the Hottel cross-string method for solving these problems. Okay, so it was not just my imagination. It was actually being taught at IIT Kanpur in 1980. Okay, that's the kind of legacy that you students are being exposed to. Okay, this is his paper. I took the time to read this paper. It is poetry. It's just absolutely beautiful. Every sentence is sculptured. Every picture is beautiful. And he's talking about furnaces and how things block radiation and how things don't block radiation. And the gas he used was CO2. Okay, so if you don't see a connection between batteries and that picture, you're missing the point, right? We may not want to make a furnace, but we might inadvertently make one. All right, well, and really, you know, to give a lecture in that name is, you know, I mean, it's not possible, right? I mean, I did my best, but that's all I did. Coming back to that lecture, so the molecular arrangements that surround ions in different solvents are remarkably similar, but lifetimes can vary by orders of magnitude. And it's that lifetime that in the end is responsible at the microscopic level for the neutral molecule being dragged across the battery. When current flows through a battery and you have an anion and a cation that's mobile, the solvent has to move. It's not as simple as electroosmotic flow. In fact, it's different, right? The divergence equation was necessary to calculate that formula that I have at least never seen in the literature. And this movement of neutral molecules is not something that is esoteric. It's like a small little effect. It is the reason why ppm has the highest reported limiting current. And finally, I say that all solid batteries will not be commercialized without soft ion conductors to allow them to breathe. And that's all. Thank you.
Questions for our speaker? Everyone's stunned.
Very nice talk. I was asking about, like, you realize that, like, this solvent velocity is important. Do you see any implications of the drag of, like, different molecules in the system in the design of next generation batteries? Maybe the drag of motion of these ions?
That's a really good question. You see, the lithium-ion battery works, okay? It's almost like you don't need to know why it works, right? If you look at the reported transference numbers, the solvent has to be moving like crazy if you use our equations. And yet it has been modeled without that, and it's fine. Where I believe what we have done is important is in where systems that don't work, like polymer electrolytes where the transport is too slow, maybe in zinc electrolytes where something is unexpected. I think that when the system doesn't work and you focus on the ions, perhaps you are missing the boat. And I would argue that in polymer electrolytes, the field missed the boat.
I see.
It's a great talk, Nitash. So, first of all, I agree with you about solid-state batteries. I've never been a fan for exactly that reason, because you have to maintain atomic contact, and anything that's rigid and solid, you can pretty much forget about it. So you need to have something soft, liquid, polymer, whatever.
You know, you and I are not very popular, right?
You know, I've been saying this for, like, I've never understood why to have solid batteries anyway, because I don't think they're necessarily that much safer either, which was the argument, because I think you can make safe liquid batteries too. Anyway, that's a separate thing.
Yeah.
So I really like this story about the solvent velocity. I guess I just want to point out that you're onto something very deep that many people have thought about, but maybe in different fields. In this department, Howard Brenner, in the final, like, 10 years of his life, actually had a bunch of papers and thought very deeply about the foundations of fluid mechanics. And what he pointed out is that if you start from, let's say, kinetic theory of gases, you can derive the momentum equation, like Navier-Stokes, where it's the mass average velocity. But if you look back at now the conservation of volume, it's not consistent, actually. There needs to be sort of like an extra equation. And so he talked about having sort of basically a conservation of mass as well as a conservation of momentum. And he said Navier-Stokes is not well defined. So even writing down the divergence of velocity 0, as you said, is not consistent, actually. And where you start to see those problems is not just in simple fluid mechanics of a pure substance, but whenever you have concentrated mixtures. And that's another place where you'll find these kinds of discussions in like really dense colloids or slurries. At some point, you know, we always say the motion of something is diffusing like in the background flow.
Yeah.
But what do you do when there isn't really very much background?
Right.
For example, even in systems like ionic liquids, what about when you have no salt?
Exactly.
So like we can't write down those equations at all in molten salts, and yet people make molten salt reactors. So there's a lot of other fields where I think people have grappled with this very same issue, and so this is one way to solve it. But
I just wanted to say that in that paper, where there's nothing pretty about it, we have mass average divergences as well as, in fact, molar average and things like that. And they are all different, but never zero in the presence of current is the way I would put it. I think the charge neutrality is a surprisingly difficult thing to envision. And yes, Howard Brenner, is a. I should, send me that paper and educate me.
Yeah, the problem is he focused on something very esoteric, where the corrections he were looking at were tiny, because he was looking at like a pure substance. What he should have looked at was, or I think anyway, is basically complex mixtures. You know, that's where you start to see these effects.
Right. No, it's a beautiful point. I sort of present results in a plain way so that I can learn about what I'm missing, because the fields are very broad, and so I appreciate that. Yeah, I would love to.
And maybe another area where I don't know if we have exactly this equation, but something sort of similar. I've been working for a long time on water and salt electrolytes, which is kind of gets exactly this issue where you have an ionic liquid, which is just salt. And you start adding solvent, but what about when there's less solvent than there is salt? So in what sense is there solvation? At some point you get to lots of solvent, and then it's like a sort of normal electrolyte or salt in solvent. So the solvent, like solvent in salt systems are very complicated, and so you actually very typically get negative transference numbers there too.
Yes.
I think your framework might be a simple way to think about that. But we're also doing cluster modeling. I'll send you some papers on that too.
Thank you.
Nitash, thanks so much for your talk. As an electrochemical engineer, I want to know what to do with this, right? So I'm going to, if you can comment on, where you would tune your polymer to actually put it in the place where the transference number is large enough so that I don't actually get fewer of these concentration effects as I'm operating at high rate. And then our part two is actually, if you look at the plot of sort of the highest energy densities over the decades, right? Those are for obviously very low rates, right? So improving the high rate capability, which I think is maybe what you're getting at, it's not necessarily going to move that envelope up, but it'll move it up more at practical rates. Is that kind of how you see it in the place you see it? So.
Yes. The first question was, where do you see practical applications for polymer batteries? Is that roughly what you said? Or?
Where would you tune your system to actually maximize the transference number, right?
That is $1
Now that
million
you know.
is not enough. I mean, I don't have a vision for that, because we've just emerged with this crazy vision that it's the neutral species, right? The molecular picture, and I don't know, Martin, if you will agree, that the molecular understanding of these things is still very nebulous. I think that jumping to AI, for example, and hoping for a solution is possible, but I'm not banking on that myself. So I don't actually know. I mean, I'm thinking of it. My students are thinking of it. We do want, in the end, an electrolyte with a higher limiting current is what we are looking for. And so that's an ongoing sort of thing. Charging rates are really, really important, very important. In fact, it's only important because we are impatient. because the discharge rates are always slow, and any battery can be discharged. So when there's a car that's driving on a solid-state battery, the first thing you should ask, how was that thing charged? And if they didn't tell you, they're hiding something. Okay? Anyway, but it's very important, which is why we've been focusing on the limiting current. It is in the end, the highest current you can sustain for steady-state batteries at steady state. So it's very important, and I would agree that we are at the front end of trying to understand that.
Hi, Professor. Thank you for the talk. I was wondering, to gauge my understanding, if the movement of the neutral solvent species is very important for the overall mass transport, does that mean that a solvent that has like lower viscosity or otherwise more mobile components would result in higher limiting current density potentially, and therefore better performance?
That's a great question. I actually don't exactly know. I'll tell you, in polymer electrolytes, the viscosity goes up by m to the 3.4 power, which is to say that you double the molecular weight, and the viscosity goes up by a factor of 20. And I can tell you that the limiting current of those two systems is roughly the same. Okay? It is not, and I was confessing to Greg Rutledge that I am not quite sure. More or less done electrophysics at this point, electrochemicals. I had to go back to polymer physics and re-envision actually what's happening. So at least in polymers, in the high molecular weight limit, it's more or less independent of viscosity. That I can assert not because I'm clever, but because my students have done the experiment. But it's a very, very good question whether that would be a tool. My feeling is that it probably isn't, because in the end, I really believe that the liquid you carry in your pocket, which looks like water if you just have it in a jar, has 100 picosecond lifetime, not one. And so obviously there the viscosity has no relevance. So how long solvent molecules stick to ions, I think is maybe independent of viscosity. I don't know. But it's a very, very good question, and you tested me on the fly, so to speak. I tried to do my best.
So in the interest of time, we're going to stop the questioning there. And let's thank Nitash once again for a stimulating talk.